Okay, we're going to have a look here at how to differentiate by using first principles. So this is basically how you would differentiate if you hadn't learnt the general rules of differentiation in the first place. All of those general rules that we use have been derived from the idea of first principles. And this is the way that it works. If you imagine that you were trying to find the gradient of this curve here at this point, then obviously the way that we would normally try and do that is by drawing tangent. If we didn't know anything about differentiation, we'd try and draw a tangent with a ruler and then try and figure out the gradient of that tangent. Well, as an approximation for the gradient at this particular point, what I could do is take 2 points that are on the curve, that are a certain distance apart from each other, and I could basically work out what the gradient of this line is between these 2 points. So I could work out what's the change in y, that's what I've got here, and what's the change in x, and I know that the gradient is the change in y divided by the change in x, so I could work out what my gradient would be from that. And what you'll see is that if I move this point closer and closer to the point that I want to work out the gradient at, this point over here, if I move it closer and closer, so go down the curve, then you can see that the line that I'm creating, this tangent, this red line here, is becoming a closer and closer approximation to the true gradient at that point. And if I get it down to here where the 2 points are infinitely close together, then that's a really, really good approximation for what the gradient is going to be. So if we now set up the notation that we would actually use for using first principles, what we do is we say that the graph that we're trying to work out the gradient of, we're going to call that y equals f of x. So it's just a general function, f of x. And so the first point, the point that I'm trying to find the gradient at, we're going to call the x-coordinate of that, we'll just call that x. And therefore the y-coordinate will be f of x. That's how you work out the y-coordinate. We then say that the distance that we're going to travel horizontally to our second point, we'll call that h. And therefore the x-coordinate of this point over here will be x plus h. So the x-coordinate plus h is going to give me this point here. And therefore I would then put that into f, so I get f of x plus h for the y-coordinate. Now from that, I can say that the change in y, because remember gradient is change in y over change in x, so change in y will be this y-coordinate here minus this y-coordinate here, so f of x plus h minus f of x, and the change in x, well, that was just h. We said that was h in the first place. We were going to call that. So it's x plus h minus x. So therefore, that's h. And that will then give us the general equation, the general formula that we use to differentiate something using first principles. So putting that together, that will then give us our formula for the differentiation by first principles. To work out that gradient, we said it was the change in y, which we said was f of x plus h minus f of x, divided by the change in x, which was this value h. And if we think back to that original graph, then for this to be a true representation of the gradient, we need to bring this point down so that it is infinitely close to the original point, our starting point. So we want h, we want that h point to basically become infinitely close to 0, infinitely small. Okay, and by making h the smallest value, an infinitely small value, then we are going to have these 2 points being infinitely close together, and therefore, as you can see from the red line there, it's a true tangent to the blue curve at that point. So returning back to our original formula, that's why we say at the front here that we're going to limit h towards 0. We want h to become basically infinitely small, and this becomes basically dy by dx. That's the notation we've used for working out the gradient at a particular point. So let's use this as an example. Let's say we're going to try and differentiate y equals x squared by using first principles. We know how to differentiate this already. We've come up with the rules, and we know that this would be that dy by dx is equal to 2x. But let's see how we can get there by using this first principles formula. So what we'll do here is we'll say, right, f of x is equal to x squared, And before I put it into the formula, I'm going to work out each of the individual parts of this formula, and then I can just stick them all in. It'll just be a little bit tidier if I do it that way. So I'll first of all work out what f of x plus h would be, because that's a pretty important part of my formula. So I'm putting x plus h into here, so x plus h squared, which is x squared plus 2xh plus h squared, if I expand those brackets. Now I can stick all of that into here. So to say what f of x plus h minus f of x over h would be, that we worked out as being x squared plus 2xh plus h squared, so I've put that into here, minus f of x, which is x squared, divided by h. And if you simplify that, well, x squared take away x squared is nothing, so that's going to go. 2xh divided by h is going to be 2x, and h squared divided by h will be h. If I now use this limit, what I'm saying is I'm limiting h towards 0. I'm imagining what would happen if h became an infinitely small number. And if I do that, basically this bit's going to disappear, isn't it? This bit part here, it's like it's equal to 0, and so I'm just left with this bit, and therefore I'm left with 2x. So dy by dx is equal to 2x, which we know to be true from the formulae that we've been using all the way through our differentiation topic.